So we get to, the discussion continues, and they get to this, and this Nielsen guy asks the question, let's just zoom in, he says, to MD Burkhardt, he says, you were talking about comparing the sound pressure at the 2 ears of the Kemar mannequin. Then you talked about differences. Have you deliberately made Kemar unsymmetrical? To which MD Burkhardt responds, no, we did not do this deliberately. In fact, we tried to make the mannequin symmetrical, but at high frequencies it is very difficult to make things exactly alike on the two sides. Up to this time, we have not found a shop that would make a mirror image mold of one side from the other at an acceptable price. We tried to make the mannequin symmetrical. I mean, this was shocking. I'd never seen this explanation ever before. This was the first time I'd seen it. And I felt at the time like I was the only person who'd seen it, because again, I don't think anybody's read this thing since 1976. It also wasn't searchable. I had to run it through an OCR utility, later just to search for keywords and things like that. And so yeah, I think there's an interesting takeaway there. This is cute. So there's a response to him by a guy named Dalsgaard. And this response is really the end of the whole symmetry discussion. But you really have to read the rest of the discussion, it's super fascinating. Dalsgaard says, I know that an organization in Denmark has developed a technique for producing the mirror image of an ear for making prostheses for people who have lost one ear. They use a special machine. I could probably give you a reference. I thought that was cute. So, what are the key takeaways here? I'd say takeaway number one is probably that Burkhardt should have probably followed up with Dalsgaard. Then we might have a symmetrical Kemar today. But the second one is advancements matter, right? I mean, this is 1976, 1972. And they didn't have any reasonable way, given whatever their budget was, to make a symmetrical mannequin. So advancements matter. I'm showing this because the very first measurement fixture we ever picked up was a Gross 45 CA we ordered in 2014. And it came with asymmetrical pinna because the pinna were based initially on Kemar's asymmetrical pinna. And I used to hound the owners of Gross for symmetrical pinna. And it wasn't me, it was everybody, I think. And so they finally made them, and they were also nice and soft. They're still probably among my favorite pinna to measure anything on, because they're so soft and symmetrical. But even though Kemar has symmetrical pinna, his head is still not symmetrical. So you'll find that the base of his pinna are still asymmetrical, but the pinna flange all the way to the drum should be symmetrical. But advancements matter, and we'll get back to that. So let's talk about hearing simulators. I'm assuming most of you at least have an idea what they are, but we're going to go over the definition. A hearing simulator is an apparatus that connects the DUT, the device under test, to a microphone in such a way that the working load on the device is the same as if used on a real ear. The need for modeling the correct impedance increases with the proximity of the DUT to the ear. So, if you're measuring a pair of loudspeakers, less important to model that correctly. Measuring in-ears or over-ears gets more important. Modeling the input impedance of the human ear becomes increasingly important the higher the acoustic output impedance of the DUT. If it's closed, higher acoustic output impedance, the more important it is. So if you have a closed in-ear, pretty important. Loudspeaker, again, not so much. There was an explanation, actually, Tyle Hertzens from Inner Fidelity, whom I think a lot of you remember because he was inimitable. He moderated a panel, and there was a really young, a really smart young engineer whom I had met when Tyle and a couple of us went to visit Philips in Belgium one year. His name was Rowan Williams, and he gave an explanation in his panel. It was a really nice explanation, very simple, easy for a guy like me to understand, and quite professorial, explaining why we use hearing simulators. He said, when you measure a speaker, you measure it with a microphone suspended in the air. And it makes sense, right? That's how we also record audio. But if you're going to measure a headphone in such a manner that you want to know what it sounds like to a person, you can't do the same thing. Now, my voice is big, so I'm going to put my mic down for a second. So, what he's saying is essentially what he says, if you want to measure a headphone, you can't do it if this was a mic like this. And even if you don't know exactly why, I think there's just looking at that, you can't do it, right? That's not going to work. And so he said, but when you want to measure something, that when you put a headphone over your ear or in your ear, you introduce an air load in front of the driver, or if it's a multi-driver, in front of the drivers. That's a fairly complex air load, and it affects the way the driver behaves. So we all seem to understand the idea that there is a transformation of the sound field from out here to the drum. I think we can pretty much get that. But what a lot of us don't understand, and I certainly didn't when I first started looking into measurements, what I didn't understand was the fact that we're also, in just coupling something to us, affecting the behavior of that driver. And if, when you're doing the measurement, you don't affect the driver in the way it's affected on you, then you're not going to get a human-like measurement. So yes, there's a transformation of the sound field, but there's also the effect on the driver. I thought that was pretty professorial. I was like, I can understand that. And if I can understand it, anyone can. To give another example, since we're mostly guys in here, we like car talk. We like cars. I have a Honda Fit. Not so impressive. A 2010. And if you were coming to me and you said, Jude, I want to buy a 2010 Honda Fit, and I'd ask you why. Why on earth would you do that? But I actually like my little car. But if you said, but I need to know what the top speed is. And I said, all right, well, here's what I'm going to do. I'm going to find out for you. I'm going to put it on a lift. Right? I'm going to lift it up. And I'm going to get in it, preferably before we lift it up because I'm so short. And I'm going to start it, put it in the tallest gear, and just floor it. Now, let's just assume for a moment that the car doesn't fall apart, like the transmission and everything. I don't throw the tires into pieces. And I say, we're going to measure the rotational speed to see how fast it's turning. Then we're going to do the calculation to see what the equivalent distance those tires at the surface would be traveled. And we say, work with me, I have no idea what it would be, 135 miles an hour. And so I go to the guy and I said, hey, you want to buy the Fit? It's going to go 135 miles an hour top speed. You're good to go, if that's what you want. I think we all know, again, just like with the microphone in front of the headphone, that's not going to work. Not the best analogy, but the whole point with the car is it's going to be a lot slower than that, because we're not introducing a load on the car that it would face its own weight, rolling resistance, aerodynamic resistance. Again, not the greatest analogy, but I think you get the point. So this is interesting. Here, this is on actually Knowles' website. You probably recognize that logo in the middle, the high-res audio logo. So the high-res audio logo is an initiative that was created by the Japan Audio Society. It's been since adopted by the CEA. It's for high-frequency performance, like out well past what we can hear. I don't know if the standards have changed. Actually, I have a friend from Audio Precision here. Tony, I'm going to ask, have the standards changed, or is it still pretty open with respect to performance at 40K for analog devices?
I don't think it has changed.
Okay.
To be honest,
so,
I don't really know.
Okay, so as the wording goes, for analog devices, to even qualify for this sticker, this logo, analog devices have to have a demonstrated capability at 40 kilohertz. That's pretty arbitrary. A demonstrated capability at 40 kilohertz. So Knowles is showing you how to do it because it doesn't tell you what the conditions have to be. It just has to show a demonstrated capability. This is literally on Knowles' website. And I understand why they do it. It makes perfect sense. So they're showing you how to measure it for high res. You take the balanced armature, put it through this baffle. The output comes out the other side. You have a 1/8 inch measurement microphone. In this case, it's a Gross, I don't remember the model. 40 dP maybe, that's what it says. But to 90 degrees to the output, measure. And then you get this, capability to 40K. Now this one's even more interesting, the bottom right, because that's, I think, one of the reference in-ears. And notice what it says. It says 100 millivolts free air at 6 millimeter 90 degree incidence. So they're measuring the in-ear in free air. I mean, just like they're doing there, but they're putting the in-ear through it. And you get demonstrated capability to 40K. But I think for anybody that measures balanced armature in-ears, you know that if you do it in situ, if you load it, you're not getting 40K. Well, all right, so Knowles is presenting tomorrow, and they have a new tweeter. I have not measured anything with this new tweeter yet. Jerry Harvey, you're the first to use these tweeters, so I don't know how they measure in situ. We'll have to talk about this. But ignoring that new tweeter, right? When this was released, that didn't exist yet, this new Knowles tweeter, which I think is supposed to have even loaded extension even to 20K or beyond. But with a normal BA, you're going to see roll off, and it's precipitous, 15, 16, 17K, and it disappears, it's gone after that when you load it. So you have to, again, if you want to know what it's like to a human, simulate what it's like on a human. That's not it, but you show capability to 40K. So let's talk about the standard that we use. The standard that we use, you guys have probably heard of 711. couplers, 711 simulators. That's one there. I forgot to bring mine down. I actually brought mine with me, one of them. And you know, we talk about the 711 coupler, but where does it come from? And so the origins of it are actually a bit of a mystery for a lot of people. So much so that that there was a group here. This is a report I found in my Google Foo. Pretty obscure report. It's ISVR Consulting, the National Physical Laboratory, NPL, what was then the Department of Trade and Industry in the UK. They wanted to find out more about these things that we're using, the mannequins, the hats, the devices, the simulators. Where do they come from? Where do these standards come from? How are they established? It's a pretty cool report. You should look at it. Well, let's look at what some of the things they concluded are. Oh, that's a little blurry. It says, in this specialized field, the standards appear to have been led by the hardware, not vice versa. It would possibly be more accurate to say that a particular standard conforms to a particular hat, not that the hat conforms to the standard. Slight deviations from and minor adjustments to the standards and revisions between different versions of the same standard suggest that manufacturers continue to lead with the standards left to follow. And then they said this about 711. The IEC 6711 1981 standard gives no clues as to the development or scientific basis of the device it describes. Although we cannot be sure, the IEC 6711 included ear simulator appears to have been based on similar impedance and dimensional data too, possibly including the same data as that on which ANSI S325 1979 included ear simulator was based. Again, this is a pretty connected group of guys, but I guess they're maybe a little more shy than me because that wasn't good enough for me. I was like, where does it come from? Turns out they were right, but they didn't have all the details filled in. So I was reading the standard. There's the bibliography to 6711, or now it's 6318-4. And I see these names, and I'm like, I know those guys. They're Bruin Care. And they were around long enough to have worked, well, especially Lars B.1. Nielsen, to have worked with this. So I contacted them and said, where did 711 come from? And they answered. And I'm just going to read it now. I know this is kind of like not good PowerPoint etiquette, but it was in a personal email, so I'm just reading a personal email. So they answered. They said Zwislocki, if you're familiar with the Zwislocki coupler, which is an old 4-branch coupler that's very difficult to work with. Zwislocki designed his 4-branch coupler based on impedance measurements of 22 subjects using a special acoustic bridge inserted in the ear canal. This allowed measurements up to about 5 kilohertz for resistance and 7 kilohertz for reactance, which was fine at the time. Again, a lot of at the time it was hearing aids. Ear canal dimensions were obtained from 7 subjects and approximated to a cylinder. Now, shame on me, I didn't look to see if J.J. Zwislocki's 7 subjects were from his 22 subjects. I mean, that could actually matter. I mean, if you look at what we're going to get into with Bruin Care in a second. This work led to ANSI S325 standard in 1979, describing an included ear simulator of the median human adult ear. It suggested 2 realizations of the target curve, one based on Zwislocki's original 4-branch design and another simpler 2-branch by industrial research. So, in the ISVR report, they actually referenced this. This was actually interesting, and I had a conversation. You know Tom Miller, Jerry, from Knowles. You know, Tom Miller's been around a long time. And I talked to him about this, and he wasn't even aware of all the little details. He's like, wow, this is great, because everything that I knew ties into everything that you're saying. I just didn't know a lot of these blanks. And so in the ISVR report, they mentioned, just as I had difficulty, that they couldn't find the original ANSI 1979 2-branch transfer impedance. It's like deleted, it's gone. You can't even buy it, which I don't understand. So I bought the most recent one. And anyway, so it says, it suggested 2 realizations, Zwislocki's 4-branch and then this 2-branch one that's a mystery. The Zwislocki coupler was, however, known to have large sample-to-sample variation and be difficult to tune due to the 4 branches. Now, by branches, we're talking about the volumes that they use to help, well, not to help, to shape the transfer impedance, to shape the response of the simulator. And so they use these branches, these resonators. Zwislocki actually had 4 of them. The 711 standard we use has 2. So
But the Zwislocki coupler was difficult because it had 4 branches and the use of something called felt metal, which I'm not even familiar with the material, to produce resistance. A more stable design was in demand. The 2-branch design in the ANSI standard was simpler in design, but used compressed cloth to realize resistance, which was not very stable. In the IEC, work was also going on specifying an occluded ear simulator in addition to the simple 2cc coupler. And in the IEC, the target curve from ANSI S325 was more or less adopted, however, with different tolerances. At Brüel & Kjær, Per Brüel already worked on a simple 1-branch design based on his own measurement and available ear simulators at the time. He was a pioneer within standardization. This is their words. And at Brüel & Kjær, a decision was made to design a stable coupler meeting the target response of both IEC and ANSI. This led to an occluded ear simulator with a suggested 2-branch realization as described in what became IEC 711, standardized in 1981. The Brüel & Kjær 4157 was elegant in design with narrow air gaps replacing metal discs, very stable and with no adjustments needed once assembled. It gradually took over the market. And this is where we go back to what ISVR was saying, that the hardware leads the standards. That 4157 from Brüel & Kjær, that 2-branch coupler, by the way, we can't find the original ANSI S325 1979. That would be the 711. They're now using that 711 to represent the 2-branch design. You can see it's similar to Zwislocki, so it was pretty easy to kind of figure out that they might be related. We overlaid those so that you could see them. They're not overlaid in the standard. But that came out in 1980, the 4157. 711 standard was published in 1981. The 4157 is still Brüel & Kjær's 711 coupler. So it was compliant all along because it established the standard. It was the first 711 coupler. It was the 4157. The hardware leads the standards. So we looked earlier, I mentioned earlier, 22 subjects using a special acoustic bridge, measurements up to about 5 kilohertz for resistance, 7 kilohertz for reactance. But we get to the standard itself, not sure how they got the range, right? Because generally speaking, when you talk to people who worked on it like years ago, or they kind of consider the upward operational range of about 8 kilohertz, not 10. But the standard shows 100 to 10 kilohertz. So 711 covers that range where it's bracketed. But that's only if you measure at the reference plane, which we'll get to in a minute. If you go further away from it, it can narrow the measurement bandwidth. So there's the one with the taller resonance is a standard 711. But here's the funny thing about this standard. The 711 standard, again, specifies human simulation from 100 hertz to 10 kilohertz. That area afterwards, that resonance that you see there, I think it's like 13.5K, something like that. That's actually specified in the standard. But it's specified in the standard to define the volume, the primary volume of the simulator. But the magnitude of that resonance, the resonance has to be there to be 711 compliant, but the magnitude is not specified. So Gross did something very smart. So one of the nightmarish things about 711 is that resonance, that half-wave resonance on the tall one there. And you'll see that with original 711 couplers. And if you want repeatability, it's very difficult to get. That thing can play havoc. So Gross said, hey, listen, they don't, maybe in Danish they said, they don't specify the magnitude, just that it has to be there. So they found a clever way to dampen. And then that allowed them to create a tolerance all the way to 20 kilohertz, plus or minus 2 dB, I believe, all the way to 20. Now to be clear, from 10 to 20, that's not a human simulation. It's a coupler. But we measure routinely up to 20 anyway. I do it. Pretty much everyone who measures with it does it. But with the RAO 402 or the RAO 401, same thing, just one's prepolarized, one's externally polarized. You get this damped response, which if you want repeatability, I highly recommend that one, if you want repeatability. But you have to know what you're seeing because it is damped. So then you have this situation with 711. And we're going to get to this and show how this kind of manifests itself sometimes. Maybe in a really key standard even, or a key piece of research. With 711, you have all these different ways that you to use it, because it was really made. It's this ear simulator, but it was made for insert devices really. But what do you do if you want to measure something else? You gotta come up with some way to couple it to it, and it was the best thing available. So they came up with the mannequins. Kemar actually came out before 711, but the 4128 on the bottom middle there, that came out I think in 1986. And when you measure, even though they're 711 couplers or 711 fixtures, you're going to get different results. And I showed this in one of my presentations here. This is a Westone W60 measured by 4 different reviewers. The ones on the top, I think, are the ones with more, let me look. I think those have more bass. Those were measured by putting it directly into the steel coupler. The bottom ones, I think, were those were mannequins, yeah. And you tend to see sometimes with the mannequins less bass, because with that steel coupler, which I wanted to bring down here, with that steel coupler, you can easily get it to the reference point and minimize the volume. So that's them overlaid at 1 kilohertz, normalized at 1 kilohertz, and then somebody asked me, I think it was Todd Welty, said, what does it look like at 500 hertz? That's what it looks like at 500 hertz normalized. So you can see some of the issues that you have. The problem with 711 and all the different fixtures is because 711 is included in other standards, like some of the ITUT stuff specifies 711 within those standards, we assume a certain interchangeability, that the results are somehow going to be comparable, but they're not a lot of the time. So depending on what you measure with, you're going to get a different result, as you see here. So I should have included that measurement of yours in here. So Todd Welty did ask me, well, maybe it's unit-to-unit variation. I mean, Jerry, you're familiar with Westone. Their unit-to-unit variation is actually pretty darn good. It's small. Certainly not like that. So I asked Warren, can you mail me yours? And darn it, I should have included it in this. I said, mail me yours, because he has his own, and we sent his, and then we measured his, and it measured very, very close to this, like when we measured it, I mean, our measurement of it. So you can see the issue there. Now, earlier I mentioned the reference plane, that's here. And everything was really made, these insert devices were made to be measured at that reference plane. Because there, the appropriate input impedance, or the transfer impedance, at that reference measurement plane, that's where, I guess you could say that the human simulation is sort of where it lives. Everything we do when we pull away from it is to move away from the reference plane. There is a measurement reference plane with the 711, and that's it. With the steel coupler up there, it's easy to push into it. You get, it's very easy to get down to it. I just realized Tal's in here. He works with Westone. Yeah, didn't see that, Tal. So yeah. And this part of the discussion brings me to this quote by Edgar Shaw that I found in one of the things that I read in my thousands of pages of reading, the External Ear Handbook of Sensory Physiology, Auditory System. This is a very important quote. Edgar Shaw is he's like a mentor to Floyd Toole, who's a mentor to Sean Olive, who's a mentor to a lot of us. Anyway, Edgar Shaw says, it is useful to divide the acoustic antenna system into its functional components, the head, the torso, and the pinna-flange acting as diffracting bodies, the concha and the ear canal serving as acoustic resonators, and the eardrum providing an acoustic termination. But these components must also always be seen as parts of an integrated system, which is hard to do with this, when we're essentially cobbling things together to find a way to couple them to a 711 simulator. All right, so we're gonna now move to the new standard, but I am running way long, which I knew I would, and we gotta get to the next step. And I've covered this before in videos. So there's like 2 videos that I did, 2 presentations I did on video, and they're these. So please, if you're interested, take a picture of these QR codes and look at them later. I'm gonna just kind of very quickly go over the 5128 standard, or ITU TP57 type 4.3. But if you watch these, you'll get more, and then I'm gonna give you other links as well to the actual study. We good? I'm gonna move forward. Gary, you wanna get that? All right. So this is a typical 7-Eleven mannequin configuration here. And that is the new standard that we're using at the office. That's the Type 5128 from Brule & Care. And you can see it's much more human-like. The typical 7-Eleven here, it's like, let's see, 7.5 millimeter by 22 millimeter tube with an equivalent volume of 1.26 cubic centimeters. That's going to matter in a minute. The 5128 is a 27 millimeter-ish long average human ear canal with an equivalent volume around 1.55 cubic centimeters. And I say 27 millimeter-ish because it's a human-like ear canal, as you can see. So how do you measure that? It's not a tube. And even by the time you get to the terminus, the end of it, which is the eardrum, and it's tilted like on a human, are you doing the most proximal part? Are you doing the center? The most distal part? You're going to get a different length, which is why I say 27 millimeter-ish. But one is definitely more human-like than the other, and I think we can see that. So the way they average Brule & Care, it took them, I think, 10 or 12 years to do this research. And they did MRI scans of 44 adult volunteers, different ages and sex represented. They used, 3D MRI scans, and they ended up with something like this. A bunch of them, 44 of them. And then they took those and they averaged them. So what you're looking at on the right is one of the subjects, and then the one on the bottom is the average that they came to. So it's, again, a more human-like than a cylinder. So the second step was to determine the average acoustic impedance, and they applied a specially designed impedance probe. It's out of order here. It should be this one here. And then they got the impedance of 32 of the 44 subjects. So they used 32 of the 44 subjects. 12 of them they just couldn't get good measurements on, so they had to discard them. That's why there were 32 subjects in the impedance study, but 44 in the canal. But the canals are so much more realistic that on a 7-Eleven coupler, when you look through it, you can see, even with a pinna, you can see directly through to the mic, even with an anthropometric pinna, because they had to adjust the canal to accommodate a fixed mic position. But with a 5128, you have to use an otoscope for the most part if you want to get a clear shot of the eardrum. Now the studies for it, I did want to mention this. Not only do they also, to get the more realism, more accuracy above 10 kilohertz, they actually had to also redesign an entire microphone. They couldn't use the half-inch microphone they've been using. So they had to design something that matched the human eardrum. And the other thing about it is, if you look here, what's really interesting is the volumes I was telling you about, those branches, they're in front of the microphone in 7-Eleven, but they are not in front over here. That way you can have the terminus or the end of the canal being there. The volumes are here, and they have these slits, these micro slits that go to the 4 volumes. That is also a 4-volume coupler because they needed more depth. They wanted to be able to get more definition for the transfer impedance, and to do that, they needed more volumes. So they went to a 4-branch coupler for greater flexibility in terms of getting the transfer impedance they wanted. Oh, and they also simulated the transition to the bone-ear condition closer to the eardrum. So it gets harder as you get closer to the eardrum, just like on a human. So clearly it's more human-like, but in the interest of time, we're just gonna have to accept that. But in the interim, there was that. Here are the studies you want to check out. And then here, you don't have to take a picture of that, you can just do this. And I included in this one the patent filing for the 5128. It's also called the 4620. If you just get the ear crinkles back there, you ordered the 4620, right?
Yep.
So that's, if you get just the ear, canal, so the pinna, canal, drum assembly, the kind of I've been showing you, you can order that separately, not need the mannequin. 5128 represents the mannequin that has the 4620 in it. You can also just buy the 4620. But there are the studies, and the patent is really worth reading, because when I talk about the reference plane discussion, it'll make more sense to you when you read the patent finally. So let's look at some measurement differences between 5128 and 711. So this is a full cal clear. It's just one seating, unsmoothed, uncompensated, not normalized. Rule & Care 5128, the new standard is in the solid line, dotted line is the 45CA. This is Campfire Audio Andromeda 2020. That's an in-ear monitor for those of you not familiar. It's a multi-driver, multi-balanced armature in-ear monitor. I think it's 5 drivers, don't hold me to it. I'm sorry, in this case, the solid line is the 45CA. The dotted line is the 5128. This is a Etymotic ER4XR, a very simple one-driver balanced armature design. Rule & Care 5128, in this case, solid. Ross 45CA with a 711 coupler is dotted. This one was interesting. That's an AKG K1000. Dotted line is the 45CA, which again, now this is a really not great scenario for a 711 coupler, because again, you're going way away from the reference plane, because it's an ear speaker type design. That is one creepy dummy, isn't it? But it is the best photo I can find to show how it's worn, and without wearing it myself. And so the solid line in this case is the 5128, dotted line is 45CA. Now the cool thing about the 5128 that I neglected to mention, I forgot, there's no measurement reference plane because of how they calculated the transfer impedance, the input transfer impedance of the canals and the drum separately. And then they kind of, if you read the studies, you'll see they kind of use one to corroborate the other. And so you have at any point in the canal, from canal entrance all the way to the drum, an accurate measurement. Just as you don't have a reference plane, or you don't have a reference plane, if I put an Etymotic straight body in here, like an ER4, in your ear, make sure I have a seal, and then let's just say that hypothetically I could put a microphone at your eardrum. Can't really do that, but anyways, let's just say I could. Or I could take the output out of your eardrum, and then we measure it, and then still again, maintaining a seal, I push it a little deeper, and then we say, now let's measure it again. There's no reference plane. It's just what it is, where it is, right? You're measuring what it's like at any given position. With a 5128 or a 4620, wherever you put it in the ear. So now, of course, when you start going to something like this, it's gonna help as well. Because again, you're not moving this far away from this area just in front of the drum that is the reference plane on a 711 that you're supposed to be measuring at. Again, with a 5128, you can measure from it anywhere. That would be technically out of the range, though, right? Because you're outside anyway. But at least you're better off because you have something that, yeah. And that brings me to this. Did you notice something about all these? This is what I added to my discussion. This wasn't in the one I gave in London. But I had to take out the Knowles thing, so I wanted to put something interesting in here. There's something interesting about these. Clear, K1000, Etymotic, Andromeda. So I noticed something. We got this thing in November of 2019, and it was December of 2019, and I was in Japan for the Tokyo Headphone Festival. And I was telling the guys the story. I was in the shower. You didn't need to know that. And I was in the shower, literally, I'm not even kidding. I was shampooing my head, thinking about these stupid measurements. I was like, what am I seeing? Like, what does this all mean? And I kid you not, I had a revelation. And so I rinsed my hair off as fast as I could. I didn't even wash the rest of me. And then I get to my phone and I call my friend Jacob Sondergaard, who used to work at Ross. Now he works at Head Acoustics. Because I really wanted to go to Rule & Care with what I was thinking, but I didn't want them to think I was a moron if my theory was dopey, right? Because I'm not an engineer. But based on the option, we did a lot of measurements leading up to this moment. I'm just showing you some. And I told my theory, which I'm going to get to in a second, to Jacob Sondergaard. And he said, no, I don't think you're a moron at all. I think you're onto something. So then I contacted my other friend, whom I'm not afraid to bounce anything off of, who's an acoustics expert who just retired from Audio Precision, Dan Foley. And I contacted Dan and said, here's what I'm thinking. And he said, no, I don't think you're a fool. I think you should go to Rule & Care with it. And I was like, all right. So I'm not a fool. So let's go to Brule and Care. So I went to Brule and Care, and it brings up this here, which we're going to get to in a second. This is the Harman target. Okay, you guys are, I'm hoping, at least mildly familiar with the Harman target. So there are two targets. There's the solid one, which is the in-ear target. We're going to go over this just, actually not a whole lot more, just time. But the dotted one is the around-ear, over-ear target, around-ear, on-ear target. And you notice that the dark one, the in-ear one, has like 4 dB more bass. And so I actually went to the AES Chicago meeting. I live in Detroit. I literally flew out there because Sean was going to be presenting the in-ear data for the first time. And I was like, all right, I got to see this. I literally flew out for that because that's what a nerd I am. So I fly out for that, and he gets done presenting it, and he just says, "This is, these are the curves. This is what we came to." And so, any questions? He gets to the end. Sean, if you haven't seen him present, he's a great presenter. And I raise my hand, and a bunch of people raise their hand, and the dude gets called on first, asks my question. He says, "Sean, you had 4 dB more bass in in-ear versus over-ear. Why?" And Sean says, "I don't know. That's just how it turned out." Right? That's how it turned out. That's just how the data shook out. And he said, though I don't know, I mean, maybe it's because over-ear headphones are more engaging, more physical, right? And so maybe that's it. We're not sure. I mean, but that's just how the data turned out. But he offered a couple of possible theories. Now that one, from the moment he said it, I had some questions about, because that's a lot of energy. If you know anything about this stuff, Jerry, that's a lot of energy to make up for here. And to say that it's because that the over-ear is more engaging, I don't think it's so much more engaging that it could make up for that. So that one was kind of tough for me. But I mean, I'm like, it's as good as an explanation as any, right? That's how the data turned out. So the big revelation I had was, in the shower, was, wait a second. Our over-ear headphones are not always, but often, especially the open ones, measuring similar in bass. The closed ones sometimes show a difference, which I should have put one up here. But the in-ears rather consistently show a difference. What if it's measurement tool related? What if it's to do with the tool? And then, so I'm going back, there's like 17 studies in the Harman thing, some peripheral to it, some directly related. And it's great work, honestly, which we're going to get to in a second. But he used 2 different setups for his measurements. He used 2 different setups. He used, one was the 45 CA with custom molded pinna. He used custom molded pinna because at the time he had the same problem we had. We had the hard Kemar type pinna on our 45 CA, and they couldn't put on-ears on it. So they molded one of Sean's colleagues' ears out of a soft material, and then the 45 CA had those ears on it. But for the in-ear, he used, I think, one of those, something like that. So now I'm thinking, okay, well, this is now getting interesting. And I went to Brule and Care with this and said, does this explain the difference? What do you think? They said, that's as good a theory as we've seen. I mean, let's look. So, and they didn't write me off as an idiot, which thank you, Jacob and Dan for. So let's get into this. This is really interesting. So I added this, by the way. That's why I'm adding it in here, because I'm trying to make up for the lost Knowles bit. Check this out, man. They set this thing up. They modeled this. That's residual or remaining volume ahead of an ER4XR. 575 cubic millimeters ahead of the tip on a 711. 750 in front of the ER4XR in 5128 or 4620. So a receiver radiating into a small enclosure will generate a sound pressure inversely proportional to the volume of the space. Less space in a 711, more pressure. And I suspect, but more tests would have to be done to know for sure. But this is my theory. That is why we have that, in my estimation. Brule and Care seems to think that's the likely explanation. I think it probably is too. Because when you start measuring in-ears, think about what you're doing. You're shrinking that volume down and you're sealing it. And so any change, remember what I said, 27-ish millimeters, 22. The equivalent volume was higher for the 5128, so therefore the remaining volume is higher ahead of the tip. I don't know, maybe I am an idiot, but I think I'm right. Sean, I told Sean about it. I asked him, what do you think? He said, that's an interesting theory. I mean, we'd have to test to know for sure. And then I asked him the other question that I thought was important, but I knew the answer would be no. I said, Sean, when you did the in-ear study, did you by any chance play Harman equalized over ears to AEOE target to the subjects and then ask them, do you perceive more bass with the Harman in-ear targeted in-ears? He said, no, we didn't do that, which of course I didn't expect they did, but man, just in the off chance that they did, I thought that would have been interesting. I mean, I guess my answer would probably be, if they perceive a difference, it would probably be less than the measurement shows, is my guess. So let's get back to this. So Sean came and visited us. If anybody has had a chance to talk to Sean, you're gonna learn something from him every time he's there with him. He's just one of those guys. And we debate sometimes, but he came to our office. That's our office there. There's Kimar, asymmetrical Kimar. And his studies, there's like 17 of them. We can't go into, it's 48 minutes, guys. We can't go into Harman. We gotta get to the next part because it's pretty interesting. I think, anyway. So everything's behind a paywall. If you're not an AES member, you're not gonna get to it. This is not behind a paywall. Sean wrote this great article for Acoustics Today, and it's free. There's the code. You can read it, and he summarizes their work. It's really well done. And what they found with the Harman target is essentially that listeners largely agree on what makes a headphone sound good. After a lot of research, and it's rigorous, and I think they could do it again, and I think if they did it exactly with the same equipment, everything else, they'd arrive at very similar or identical results. And that's one of the hallmarks of a well-structured study. It's probably one of the most important types of work that we've had in the space. I think it was a great gift to the community. I can't believe Harman allowed that to be public knowledge. I teased Sean a little bit. I think when we were at one of the AES events, I said, when is Harman going to start incorporating your stuff? I mean, as it is now, you're like doing open source. They're paying for you to do open source research for everybody else. And now they are incorporating it. So it's super duper valuable, but I still have a problem. And that problem isn't with Sean's work, it's with how we use it. We're going to get to that in a second. So what's happening now, I think, and I'm going to say it, I think reviewers are reviewing measurements today, a lot of them. They are reviewing measurements. They are reviewing what they see. If I see a review and they say kilohertz and hertz all over it, I'm sorry, man. I have decent hearing. I'm pretty good. I'm all right on that Harman. Anybody do the Harman how to listen test stuff? It's pretty fun. I can't get 100% on that. I'm not a human FFT, for the love of God. And so I'm not a human analyzer. But I see a review and you're listening to music and you're saying it's hot at between 1.5 K and this K. I'm like, and then I know I'm going to find a corresponding measurement. And I was at an audio show and a reviewer was measuring at the show. And the reviews, hertz, kilohertz. And I think as reviewers, we're getting to the point, not that I'm a prolific reviewer anymore or ever, but I think we're getting to the point where we're afraid to not go with a measurement. We are afraid of our ears. And I have a problem with that because the Harman target, which I think a lot of people are married to now, is, again, probably the best available research of its type. I have no doubt about that. A tremendous gift. But, even they say, some of Sean's quotes, these findings suggest that a single headphone target may not be sufficient to satisfy variations in the recordings, individual tastes, listening experience, and hearing loss. Another guy in a recent exchange actually resolved, I think you were commented on it, was that Reddit thread on the Harman target. And then some guy said, Sean says that everything is supposed to sound like this or something like that. And Sean responded, he said, I've never said it's perfect for everyone. The OE target, the over-ear target, was preferred by 64% of the listeners tested versus the other 30 headphones tested. 64% is not everyone, and any study is limited by the sample size. It's a good reference or starting point. And I agree completely. If I was starting a headphone company today, and you said, Jude, how are we going to voice this thing? I don't know, man. I've never made a headphone before. Why don't we start with the Harman target? That's what I would start with. It's great research. But is it exactly what all of us want? And this is how a lot of the activity I see, or how users are assessing it. Because here's the thing, if you want something that matches the Harman target, buy an AKG K371. Of all passive headphones, it probably is the closest thing to it. And it's a good headphone, by the way, for 170 bucks. Really good headphone for 170 bucks. But is it everything? I don't think so. We're going to get back to this because I really need to get to this next one. And I'm going to give an example of reviewers counting on measurements too much, in my opinion. And by the way, and obviously we measure. We do thousands and thousands of measurements. I don't think there's a company in there. Tal, we talk measurements with Dave, Jerry. We've been talking measurements since the beginning of time. And probably most of the companies in there I've either done measurements with, shared measurements with. I've even helped some of them set up their measurement rigs. You know what I mean? And so obviously I believe in measurements. I just don't like what I'm seeing as far as how reviews are reviews of measurements more than of the earphone.
Preach.
So I like the stereophile old model, which John Atkinson would measure something, and then somebody would review it, and then people, and then subjectively, and then you'd say, whoa. Sometimes it matched up because they didn't work together, and so sometimes you'd read it and go, this one does not match the other, but that's okay. You know what I mean? So anyways, let's get to this one. You guys might be familiar with this headphone, and I apologize. I'm going to try not to run over time. But that's why they gave me the last slot, because I've been running over time. So that is, we'll order dinner? No, I'm joking, we're not ordering dinner. So there's the AirPods Max. That's Apple's first over-ear headphone. It's not an audiophile headphone, but I like it. Anybody here have a pair? I like it. Anybody that has a pair, do you like it?
Yeah.
Okay, I like it. Is it an audiophile headphone? Is it my standard? No. It's probably one of the most technologically advanced headphones in the world, though. So, okay, I have to go back a step. So something happened some years back. I'm moving fast, sorry. There was a headphone that was released by Sony. It was their first generation good noise cancel. It was called the MDR1000X. Now they're called WH1000X and 2X and 3X and 4X and 5. So the first one was the MDR1000X. Sony sends me one just before I'm going to Japan. So I'm like, beauty. I got this headphone. I'm going to compare it to my QC35. I'm getting to a point here. So I'm going back and forth between them, and the guy next to me says, if you don't mind me asking, what are you doing? I said, I'm comparing these two noise cancelers. And he's like, I go, you want to try? He said, yeah. So I said, tell me which one you think cancels more noise, the black one or the silver one? The silver one is the Bose. And he said, he does it, and we're trading headphones, right? So now we're switching. He's, are you ready? Yeah, so we switch. Never met the guy in my life. And he said, the black one for sure. I said, the black one? Hallelujah. Somebody finally beat Bose, right? Sony beat Bose. I was super excited, right? I literally was so excited. I did something that I'd never done before, and I haven't done since because I felt like a moron. Holding my phone up, I recorded a video on the streets of Shibuya going, hallelujah, somebody beat Bose, essentially, right? I mean, it's probably not a great video, but anyways, I was really excited. So fast forward, Head Acoustics, I think they saw my video, they were like, okay, and then the reviews had come out after that. I think we were probably the first ones to say it beat Bose, because we were probably one of the first ones to get it and fly with it. And so, Jacob Sondergaard there, he says, you know, we at Head Acoustics, we're going to do a study on this ANC thing. So they did the MDR1000X and the QC35. And he presents this at Alma, 2000, whatever year, 18. And so I hadn't seen the data yet. So if you're not familiar, Head Acoustics does the high standard for an ANC measurement. And I'll get to that in a second. So they do the study between those two headphones. Guess which one canceled more noise? The Bose, by just a little bit in terms of pure FFT. On a pure FFT basis, as an analyzer would see it, The Bose canceled just a little more noise. But the Sony, when it came to human hearing modeling and human preference, canceled more noise, just edged it out. So they just edged each other out. One, in terms of pure FFT basis, and the other, human. So I'm like, this is amazing. So, so essentially, now we're factoring in something that I think is interesting, which is psychoacoustics, which I think we just ignore too much. And essentially, the one, if you looked at it on the pure FFT basis, you'd say, okay, well, one cancels more noise, it wins. If you're an analyzer, but as a human, the Sony canceled a little bit more noise. I think the Sony, I don't remember which one had, I think it had slightly higher passive. All right, so let's get to this. This is how they test them. So because he did that, and then the AirPods Max, we got an AirPods Max. I also have a K371. I'll say it now, I think they're both good. I tend to prefer the AirPods Max as a general use headphone. I like the K371 as well. It's pretty close. Neither for me are like what I'm going to turn to when I want audiophile stuff. But the AirPods Max is kind of hard to put away because it has good mics, good noise canceling, amazing pass-through, which we'll get to in a second. So the way they test, when you see a reviewer, so here's the other thing. With the AirPods Max, if you look at the tech reviewers, they're like, I like the way the AirPods Max sounds. Almost all of them do because they don't measure. But the people that measure don't like it. Big surprise. We're going to get to that in a second. So there's a head acoustic setup. We call that affectionately, I don't have one, it's too expensive. We call that the Predator, because it looks like dreadlocks up there. And they put that up there to calibrate the head in a position. Because when you watch a reviewer and they test ANC by turning on their computer speakers, it's probably better than nothing in playing airplane sound. But in order to really understand how it's going to cancel noise, you have to recreate the environment and the time domain information, the whole thing. So if you calibrate it, the software calibrates the dummy to the position, right? Like you put it in the position, as long as you get in a reasonable position, it'll then calibrate and puts him in the proper time domain, where they have recordings where they recreate the airplane, street corner, cafe, maybe train, maybe car, something like that. Don't hold me to it. You take the dummy off the chair and you sit there after they calibrate it. You move yourself into the location. You're in there. You're in the plane. It's pretty cool. But it's a small sweet spot, so you lean out, you lose that totally immersive effect. This is very important though to do if you want to test it correctly. So they do that, and it's a surround array with a subwoofer. And where'd my slide go? Let's see if I can play this. See if you can hear this. So what happened was, I wanted to test a bunch of ANC headphones. We'll probably put this data out at some point. And so I think we spent 4 days there. Brian was with me. I don't know if Brian's in the room. We were there for like 3 or 4 days testing these headphones. These tests aren't short. And this is what we got. So this is the AirPods Max. This is interesting. I don't know how to read that anymore. I have to look at the key every time I look at these because I'm not used to looking at these measurements. But the top one is ANC. Between the WH-1000XM4, AirPods Max, Bose NC700, I think a Shure, a Bowers & Wilkins, by a hair, it wins. That's the AirPods Max ANC on the top, it wins. And the funny thing is they asked us to call it. They said, what do you think before we test it? What do you think is going to come out number one? So, because I can't test ANC like this at home, and they're 30 minutes from us, which I'm very lucky. They're a German-based company, but their US headquarters is like 30 minutes from our office, which is great. And I asked them if we could employ their services. They're like, we could probably use this information. It could be fun. So we went over there to do this. And so that's ANC wins by a hair over XM4. And we guessed either XM4 or AirPods. We weren't sure. But then they said, what do you think will win for outgoing voice? And I said, what did I say? NC700, because we talk on the phone a lot, and he helps me test them. And he always says the NC700 sounds better than the other over ears. So I said NC700, AirPods Max next, everything else would be fighting for peanuts. And that's how it turned out. It came in second to the NC700. And the way they do it is they make a call through a closed loop cell network. They have some very expensive test box that can do a closed loop cell test, where you have a phone and then it can test it through a phone properly. Comes in second. Now this one's interesting. That is transparency or talk through mode. And getting talk through is a huge challenge, and we take it for granted. Any of you Apple AirPods Pro users or AirPods Max users, when you put it in transparency, see, like right now, if I had a transparent film in front of me and you didn't know, and I pushed on it, and you said, "Oh crap, we didn't see it. I didn't notice." That's because it's transparent, right? So transparency, the reference is no headphone at all, and what you're measuring, LE, is listening effort, okay? And then you heard the talking, and then they're playing different noises, and then they assess it in different environments and everything else. The AirPods Max crushed everything. There was no close second. It just destroyed everything in the over-ear space. Nothing came close. Have you put on the AirPods Max in transparency mode? You take it for granted because you say, it just works. And then you put on somebody else's and you're like, that doesn't work so well. But I can hear stuff, I can hear things. I had one in-ear, I think it was Soundcore's first in-ear. I remember I would turn on the transparency function and I could hear these teenage girls talking that I could not hear without them. I was like, okay, that's not natural, but it's interesting. So anyway, so transparency, the reference is nothing at all on your head. And it crushed everything. Why is it so difficult? Well, you have to process, this is super complex, think about it. You've got speech and noise, you've got to then discern all this. And here's the amazing thing with the Apple, the time domain performance. That's what we take for granted. If I'm behind you and you're wearing an AirPods Max, you will know, right? You're not gonna look like in the wrong, you can close your eyes, and if I say like, Warren, he'll look in the right direction. Somehow it conveys it, which is why it's so convincing, right? You just forget they're on. That is so difficult to do because you've got to compensate for the presence of the headphone on your head amidst all the speech and noise that you're trying to process. Get the time domain information right for directionality. I don't know how Apple does it, but they do it. And they crush everything. They also have Atmos surround support with head tracking. Okay, it's a really advanced headphone. Can we accept that? So it can do all this. It can beat the WH-1000XM4, edge it out in noise canceling. Yeah, I don't think it'll beat the XM5 though. We were testing it on the plane right on the way here. That XM5 is pretty ridiculous for noise canceling. We didn't have it at the time, it wasn't out yet. And it gets second place in outgoing voice by a hair. Crushes everything, and the hardest thing to do, but we're supposed to believe it can't get basic, just basic. Sound quality right? You don't have to love it, but is it really terrible? Without EQ? I don't believe it's terrible without EQ. Even worse, he says with EQ, the sound becomes very good, prompting me to recommend it such. How good, I can't quite tell because I can't get enough volume on Windows. It can range from good to great with the EQ settings, and there's these EQ settings. I won't mention any engineers, but I shared the EQ setting with an engineer who likes his AirPods Maxes, and I showed him the EQ settings, which are based on the measurements. And he said, why would I want to do that without even applying them? I have applied them, and I'm not going to say much other than that I didn't like it. I'm not trying to rag on this guy too hard. And you might like him. Who am I to tell you you shouldn't? I'd be surprised if you did. But we're talking Q at 2, at 2,000 hertz, up 5 dB, at 4, up 8. So here are the measurements, and I said, does he have a bad measurement? We have a 45 CA, and the thing is, like a year and a half ago or 2 years ago when we got it, we measured on 45 CA, but here's the difference. We got this measurement here, and I realized it's exactly like his measurement. It's exactly like his measurement. And so clearly he got a good measurement on a 45 CA, which is a bad measurement as far as humans go. It doesn't like the 45 CA. It has a host of sensors in it. I don't know exactly how they work because Apple won't tell you. But it does, we know it does some kind of active EQ. The HomePods also do kind of EQ. Like they have I think a gyroscopic sensor in them. If their smart speaker, if you move it, it says, oh, I've been moved, so it re-EQs for like the next 10 minutes. They're into this active EQ thing. And so we did our measurements the year, and so we confirmed. But here's what I concluded when I saw my measurement. That doesn't sound like what I'm hearing. Because remember, we were in a race to try to get the first. We said, let's get the first. We never post measurements first. Let's put our AirPods Max measurements up. Since it's like a big headphone, let's get some Google juice. And we go to put it up. I measured on 45 CA. I said, we can't use those. That will not work. That's not what it sounds like to me. And then I saw these. See, this measurement is on ratings. And again, I'm not trying to, you know, I should have probably anonymized them. But anyways, that measurement there, that chasm that he's getting, is similar to what we got in our first 5128 measurement. Now, ratings is pretty open about the fact that they review largely their measurements. I mean, there's an honesty, I think, to their approach. They assess it based on the measurement. This is our official measurement that we published. And even this, which was the best measurement we could get, I still don't know that's what I'm hearing, but that's okay. I mean, that's the measurement. And what we found, though, when we first ran the measurement, were those dotted ones, which kind of look like ratings. There's ours. There's the dotted ones. So what I did is I contacted some people. All I can say is there are people that should probably have some familiarity with the headphone. That's all I can say. Showed them the measurements in the dotted lines. Got some quick responses. Yeah, that shouldn't be like, it shouldn't be like that. And I was like, all right. Got a couple of tips, and we eventually ended up with this one. When I sent that one to them, didn't get any responses. They were pretty quick. They were pretty quick on the bad ones. So I'm thinking maybe that one was acceptable at least. But the one thing that was clear in our communications was, your mannequin's not a human. This headphone's made for humans. And this is where it gets complicated with these types of headphones that do EQ. They have sensors. Resolve. Andrew, I was just reading one of yours where you had to cover a sensor or something, you know, to trick a sensor to thinking it was being worn. But when you get something that's now using, what methods is Apple using? I don't really know. So if you remember, there was something called True Note with AKG. It would do a sweep in each ear, and then it would calibrate. Is it doing something like that using music as the source? I don't know. I have no idea what it's doing. But it definitely EQs, because it's easy to get that response. There were others that looked like that as well, the dotted line. So this is, again, the Andromeda 2020, 45 CA dark, 5128 dotted. There is our 45 CA measurement dark of the AirPods Max versus our 5128. Remember that one. Look at it next to the other one. Remember this one? That one, that one, that one. That's not a good measurement. Something's wrong here, right? That's not, and I know I don't hear it like that dark line. So this is the Andromeda 20. I shuffled my slides, sorry guys. That's the Andromeda 2020 versus Harman on 45 CA. But remember, this is what it looks like on the dotted line with our 5128. So this is another interesting thing. Oh, so getting to Harman, this is Oratory 1990, did this. He works for this company here, and he showed the preferred bass response of in-ear headphones using Sean Olive's data. He's really good at the statistical crunching stuff. And so 90% confidence interval, what he's showing is that, you know, to get 90% confidence, you know, you have this big wide range here. And so they have their own curve. They modified Harman. Looks like lower upper mids, more flexibility in the bass, earlier onset from the mids. Here's the Andromeda 2020. I like this piece. So this gets kind of interesting. So head acoustics, All right, we're 10 minutes ahead, over. I understand if all you get up to leave, but I'm gonna keep talking. You can get up to leave anytime you want. So and I won't be offended. So Head Acoustics, who does a lot of stuff with human hearing modeling, contacted me and said, hey, we've got this thing that you might be interested in called multi-dimensional audio quality score. And it uses human hearing, it uses jury test data. It's separate, totally separate research from the ANC stuff and the speech quality stuff, which also has a lot of human hearing modeling stuff in it. Would you be wanting to try it just to see what you think? And I said, yeah, I'd like to. Why not? I'd like to try this. And so let me see if I can get to more about it. Sorry, guys. All right. So this is just, I'm not going to get into it because, you know, we just started playing with it with them. They came over with a pre-production version of it. And it measures MOS-T, which is timbre, that represents the spectral properties of the transmission system and the temporal resolution. That would include the frequency response target. And you can measure anything with it. Well, okay, not anything. Car audio, smart speakers, bookshelf speakers, and headphones and earphones. I think pretty much anything. So then it does MOS-D, distortion, nonlinearities, and additive noise. MOS-I, immersiveness, represents source width and source position. Reproduction of the signal's temporal structure, which is important for spatial perception of the audio signal. Comparison of spectral content in the upper mids, which is very important for human listeners. Binaural hearing model. 2 variants of differences between correlograms. This model qualifies the spatial perception of the human listener. And for this dimension, immersiveness in particular is where we see the use of advanced binaural hearing models that go beyond the human eardrum. We model both the cochlea fluids and hair cell movements to end up with neurological path predictions to create correlograms that are used in multiple ways to quantify the spatial perception of a human listener. So they came to my office and they said, "You want to do this?" I said, let's play with it. And so they bring it over and we start measuring. They said, "What are we measuring?" I said, "Well, what do you think I wanted to measure first?" I wanted to measure the AKG, K371, and the Apple AirPods Max. Because the AirPods Max gets kind of, destroyed by reviewers in the audiophile world, liked by tech guys, and the K371 gets praised by those in the audiophile world because it matches the Harman target. I like it too, by the way. But I do know one thing. I don't like the AirPods Max that much more than the K371, and it certainly is not terrible compared to it, in my estimation. You might feel different. So I said, let's start with that, and we did. We measured it. Guess what the result was? The AirPods Max came out at like 4.7 MOS score, and they run 6 music types that are controlled. They know what these are test stimulus for them, but it's real music, and then they play sweeps, test tones, and then it mixes in with jury test data. Now the thing you need to know is the jury test data is based on inexperienced listeners because they're trying to make stuff that appeals to everybody. I would hope that someday they would do it with more experienced listeners. So to fast forward to another result, the HD800 scored well, but not as well as either the 371 or the AirPods Max. Why? Bass, right? In independent research by just about everyone, Paul Barton, Phillips, Harman, people like their bass. And in the general market, have you ever rented a car with a bass and treble control? Has the bass control ever been up? No, it's always to the right. So we like bass. So an HD800 would be considered lean to the average consumer. It's going to lose. So I would like to see them do this with a jury test database of experienced or audiophile type listeners. Maybe. So then they bring over, and the reason the Andromeda 2020, that was the highest scoring of anything that we tested. We only tested a dozen devices. And I was like, that's interesting. I just grabbed they said, grab what you like, right? Let's see how they do. And I said, the Andromeda 2020, it's a safe in-ear. Almost, when it came out, just a lot of people liked it. It was a safe in-ear. And that scored like a 4.8. Again, inexperienced listeners, not audiophile, but audiophiles like it as well. Then they brought over a production version for us to test and got similar results. There were a couple of shifts. They changed some things. But this is where I have to say, I don't know if they're onto it. I mean, we're going to keep playing with it because I find it interesting. We're going to have to explain it because when you get a number score, a MOS score, it's kind of reductive looking. But man, if you know what actually goes into it, it's really complex. So I'm curious about it. So we're gonna keep measuring with it from time to time just to see what we think. But here's the thing. So Sean was here. This is one of the little points of debate we had. He says headphones are mostly minimum phase devices. So the time domain information, frequency domain information, it's in there. So when they asked him here, actually, I think maybe it was here, yeah. They said, what do we have to measure, Sean, when we measure headphones? He said, frequency response, frequency response, frequency response. So that would, I agree, be number one. And somebody asked about time domain. He gave the answer about minimum phase devices. It's in there and should be included. All that information's in there. Bad time domain performance reflecting the frequency response. I told him, I raised my hand. I said, I don't agree fully with that. I think there's more to it. And let me explain this and I'll let you guys go because I'm keeping you late. But I want you to just think about this for a second. So I said I think there's time domain, binaural type stuff that we need to be aware of, right? Dan Foley, who's the acoustics guy who just retired from Audio Precision, also said I think time domain stuff is there. We just have to figure that one out. And when you think about the frequency response thing, if you think about what we're doing when we're measuring drum pressure as a function of frequency, right? That's what we're doing because we're simulating the ear drum. We're measuring drum pressure as a function of frequency. So if we're right and everything we need to know is just in the frequency response, then you can take a headphone like a Sennheiser HD800 or HD800S, which always, unless something went wrong between when they shipped it out of the factory to when it comes to you, the customer, it's going to measure symmetrically. I know this because I've measured a zillion of them. Okay, not a zillion, nine of them. So, measured HD800Ss. I even did a presentation in London where I showed what happens to the distortion spurs. So just like measurement microphones, the sensitivity is not always equal between two different pairs, but they do multi-parameter driver matching across a pool of thousands of drivers. And so by the time the computer spits out the matched pairs, they are so matched that I actually showed what happens when you turn up the distortion, like turn up the volume, give it more power, and then distortion spurs go up. They go up the same left and right. It's pretty insane, but it's different from another pair, which also then has a left and right that does it. And I was like, that's pretty impressive. They're pretty good at matching these things. And okay, so Dan Clark, SoCal, a lot of these companies in there, they do multi-parameter driver matching. So they're going to get similar matching results. The pads throw something into it. The reason the HD800s and HD800Ss are particularly good for this is because they have low deflection ear pads. Ear pads can wreak havoc with position. You have to get it just right. So measuring both ears helps at the same time because then you can monitor both. So now if you give me this, that a Sennheiser HD800S is symmetrical, left and right, any one you have, as long as it's new and it's functioning and it hasn't been broken in shipping, then you believe, right? Or then all you have to do is run a log swept sine through it, one channel, because you know the other channel matches, and you know everything you need to know about this headphone. I can't buy that. See, that to me, there's a disconnect for me. I mean, maybe you think that that's enough. Paul Barton and I were just discussing this, and we had this hilarious debate going back and forth. It turns out we agree more than we disagree. But I don't think that simply running a sine sweep through one channel of a HD800 tells me everything I need to know about that headphone. There is more there. So, anyway. Don't look for the easy answers, listen to some headphones. You got a bunch in there. Listen to a bunch of headphones. If you start seeing kilohertz, hertz, and whatever in my reviews, no, I started counting on my measurements. You know, and it's like, oh, no, seriously, watch mixing engineers. Anybody mixing engineer, work with mixing? I mean, I've been at studios and you don't see them say, yeah, we're gonna change it to 2.2K, right? They work ranges. They kind of know where to go, but it's not like, well, Jerry, there you go. You know, we're not human FFTs, most of us anyway. Maybe some of us are. I'm not. So, I don't know. I'm not saying trust your ears solely, that measurements don't matter. I mean, if the measurements didn't matter, why would I be doing thousands of them? Clearly, I think they matter. But my issue is not with the Harman target, not with the fact that we measure. It's the fact that I think reviewers are reviewing measurements today, too many of them, and we are believing everything they say. Listen to the headphone. I saw the 45 CA measurement. I saw my AirPods Max measurement on the 5128. I knew it didn't sound like that. I contacted people to say, why am I seeing this? We didn't just rush and put the measurement up. Because I'm not a human FFT, but I knew I wasn't hearing that. So anywho, I kept you for way too long. I am so sorry. Any questions?
Thank you. Great talk.
Thanks,
but I have two quick questions.
Sure.
One is, I think I missed something. So when they designed the 711 coupler,
Yeah.
you said they measured impedance and resistance.
Yeah.
So wouldn't that account for the pinna and other external
No,
factors?
they're using an impedance probe, so the pin is not engaged when they're doing that.
Okay.
Yeah.
So then I thought maybe they were essentially counting the pinna twice. once
No.
once from the device that they then took the data and made, and then they're sticking it again in a pinning. So no, got it. And the other is, you mentioned that when you're measuring these things, you really you want to measure the impulse at the drum, right?
We're not measuring the impulse per se. I mean, you can derive the impulse response from the like from the Fourier transform from
but
the
everybody has different canals and they hear differently too. So there's a medical test where you can present a click or a tone, and you can actually measure the brainwave and tell them to hear it. And
see if you even responded to it.
Yeah. So now with AI and machine learning, you should be able to tell how they hear, compare it to a headphone, and actually get rid of most of the stuff between the outside and the inside, and tell how people hear and use that.
If I tried to answer that authoritatively, I'd be pretending.
Okay.
So I don't really.
But it's a good idea for future research.
I'm not sure. I'm sorry, Doug. I wish I could be able to help you.
Is there any more critical questions?
Yeah.
So this talk is mostly around ITU-T type 4.3.
Yeah.
But I would like to pick your brain on what you think on ITU-T type 4.4.
I knew somebody was going to ask that. And no, we did not set this up. I swear to goodness.
Very good.
So, head acoustics. So, for those of you who don't know, head acoustics, the 4.4 is actually validation of Rule & Care's work, because it is essentially a subset of 4.3. Now, they do make reference to a reference plane, because in that case there is one. It's essentially a modified 711 with more, I think it has more back volume to make up for some of that additional volume. Yes, we tested with it, so if you want to see some measurements, I can pull a couple up. So, it's not exactly the same, because there is a reference plane with that. So, but it validates the fact that head acoustics is saying, we're going to use, so what they did is they used, up until their reference plane, they have the same canal dimensions as 4.3. They're using the canal data from Brule & Care, right? Now Brule & Care says, here's a reference plane, because they have to produce a transfer impedance. What are you going to do? Produce 1,000 transfer impedance curves? They pick one. So they choose a place, I'm guessing, I don't know, but they choose a place that's far enough that you're not going to hit it, right? Where they can then plot from that point, that distance. It's not just distance, because you have to do, remember, it's not a cylinder, so you have to figure out where it is within that human canal, like the azimuth and all that other stuff. Again, if I pretend I know what I'm talking about in great detail, I am pretending. So, but yeah, so they have a reference plane for the transfer impedance, 4.3. But for 4.4, that is where that's idealized. Do you see what I'm saying? Because it's a subset. They're not going all the way to the drum. So here's the 4.4. Let me find it. There is, let's go to presenter mode. That is an Etymotic ER4XR, I believe. I think that's an XR, yeah. That is 4.4 and dotted line, 4.3. 5128 is a solid. That is an HD800S, 4.4. This is unnormalized, and I use 80 dB white noise to set level. Solid line is, here, let's just do the average. There's the average of the 5128 in the dark versus the individual seatings of 4.4 on the dotted line. I think that's all I brought. But yeah, so it's not exactly the same. But it is further validation of Brule & Care's work to develop 4.3. Head acoustics would not use it if it wasn't good.
So all of the couplers we've been talking about are backed with air behind the measurement plane, right? They have air. The human ear has a liquid behind our eardrum.
Yeah.
Shouldn't that be something that we take into account with these?
Yeah. Well, that's kind of what head acoustics is talking about with MDAX. Mm-hmm. Because at the end of the day, so this is an interesting one. So Andrew Bright, who's with Apple, was probably the best presentation of any type at 2016 AES Headphone Conference in Aalborg. And let me see if I can find what he said. He was like the best. Let me see if I can find it. I think it's back in the canal thing. And because I wanted to say it, but I missed a lot of stuff because I don't present a lot. Let's go back to that. So Andrew Bright talked about this, and he did a systematic review, a meta-analysis, I guess you can say, darn it, about he was trying to determine, do we need to measure beyond the eardrum? The physical part of it, right? Or is it enough to stop at the drum? Because he figured maybe you had to go past it, somewhere toward the cochlea, right? Mm-hmm. But what he found, because I can't find it now, is that using a lot of work from Herbert Huda, found that the eardrum is largely reflective above 3 kilohertz. I'm simplifying. Determines you don't need to measure beyond the drum. The drum pressure is a good estimation of hearing. As for the rest of it, right, when you're going to model it, like Head Acoustics is looking to do, you really are stopping at drum pressure. Everything else after that is probably going to be in software, is my guess, right? Modeling it in software. Yeah.
Continued question on top of that, though, shouldn't there be reflective waves coming back through that liquid on the other side that would then impact the noise back on the other side of the eardrum? Because then at that point the eardrum would act effectively as a speaker itself.
Yeah, once again, that's another place that I would have to like BS and pretend I knew something I didn't. I won't do that.
It's not, the eardrum would stop that.
No, I appreciate the question though. I'm sorry I couldn't
yeah,
answer
yeah,
it. That's all I'm
yeah.
saying. Yeah, I'm sorry.
Yeah.
Man.
Because the
So
liquid's on
a while ago,
Oh, hold
Sean,
on 1 second. Doug.
Oh, sorry. Sean and I were talking a while ago about some of the mischaracterizations of some of his research, or the narratives or trends that you see online about the way that people are not just evaluating but also reading some of the measurements and coming to the conclusions that they are.
Yeah.
And we were talking about maybe like different papers that could be made public in different ways that might be like rather than behind the AES paywall, to maybe help with some of the misconceptions, right? And maybe help fit things together a little bit better. And we sort of thought maybe the segmentation paper would be a great way to do this, to give a sense of it's not just this one thing that everybody's.
Oh, the user segmentation paper?
The Ahmed, or the Qatar report, Welty, and
Yeah. You know what I find the most interesting about that, and it's probably a sample size thing,
Yeah.
was when I saw that 0% of experienced listeners wanted less bass than harmony. Zero.
Yeah. So what I was wondering though, given the sort of the spirit of some of the what you just said here, is there something else that we should be considering other than just making additional research public to help with some of the narratives that might be forming even as currently?
Oh gosh, I don't know, Andrew. I see. For me, I'm like endlessly curious. I'm like a high functioning whatever when I'm talking about this stuff, and I obsess about it like while I'm in the shower, and so I don't know the answer to that. So what I am constantly doing is just trying to learn more, because again, I'm not an engineer, and so that whole reference plane discussion, I contacted Soren Janssen and Lars B. Nielsen again, and I asked them before I presented on the Human Hearing Simulation Evolution talk. I said, can I ask you something? They're like, yeah, what's that? And I said, if I'm getting this correctly, there's no measurement reference plane. And they said, I know there's a reference plane referenced in the how you did the impedance study. You propagated to to correct for the smearing of the resonances and the impedance. But by the time you get to it, there's no measurement reference plane, is there? And they were quiet, and they said, we never really thought about it like specifically that point, but you are correct. There is no measurement reference plane. And they said, you always ask questions, and it's because I'm not an engineer, probably. Like, the moment in the shower, I'm just thinking about what I see. And so then I have to ask questions. And so I read anybody that works with me knows I read way too much of this crap. My wife knows I read way too much of this stuff. I don't even know why, but I'm trying to just get to my own understanding of truth. And then, I kind of couple it with, what's interesting is to couple it with the data that you see, what I call data of users on forums, on chats, and what they're saying. But now I feel like it's getting complicated, because I feel like a lot of them are being unduly, just overly influenced by the measurements. And it's like now it's hard to find the legends based on actual what they like as much as what they see. And that's so So that's getting a little bit more troubling, because back in the old days, right, you can kind of get like what the, Sennheiser HC650, people generally like that a lot. You can kind of see, so that's getting a little bit more difficult. But to answer your question, I don't really know. I mean, so for me, obviously, I think you can tell, I'm obviously always pursuing. I don't post a lot about it because there are times I'm uncomfortable with how it gets used by the time it gets to the user who doesn't know. So for example, even looking at where you normalize. Did you notice something? If you watched any of my videos, the last couple ones, I say, this is what it sounds more like to me. And I've been slagged on for normalizing where I want to normalize. But guess what? Matching it one frequency, right? Which is why we use noise now. I don't even know if we're going to stick with that, but I'm trying to find something that's more representative of just using a single tone, whether it's 1 Pascal at 500 hertz, 90 dB at 1K, and just lining it up there, and then people making comparisons. And you only make comparisons in a very absolute rudimentary sense. So they'll say, oh, so this one has bass that's higher than this bass, so it has more bass. It's not that way. I mean, it's all about the balance, and people don't understand that. And so that's why I struggle with this. Because we do thousands of measurements. We're doing it. Critical just told me, he goes, hey, we have an open source, our measurement tool is open source, because we're coding our own right now, right? And I'm like, I mean, we're gonna put them out there at some point. We're gonna put, but I'm not gonna lie, I'm having some difficulty with this. We have thousands of measurements. You talk to anybody, almost anybody in that room that makes a headphone, we probably discuss measurements, shared measurements, yeah.
Should we just be using compensated measurements to maybe combat some of the problems of, maybe misconceptions around that?
I don't know. I mean, the whole compensation game, was kind of ridiculous back in the day when we were measuring shoe boxes. And toilet paper rolls. But I don't know. I'm not sure how I feel about that.
Is there a reason for comparing measurements? Why we don't do like a best fit or something like that instead?
What do you mean?
So like in like other data comparison, you can do like linear regression or some other kind of best fit. These are just point clouds, effectively. Like, why can't we do a best fit between those point clouds and
you mean with respect to where we normalize it?
Yeah.
No, that's reasonable. That's a
some
reasonable
frequency.
question. But then you have so for example, right? You have to think about where you're normalizing it, right? Because where we're most sensitive, like where we hear, for example, where we're more sensitive in one area than another.
Mm-hmm.
I get where you're going, and yes, I think it does. I don't think it's going to be this universal, like 1 point all the time.
Mm-hmm.
So we went with noise because, I'm just basic enough that I need to go with something that I can do as a matter of routine. But even then, you saw. I'm assuming you saw. You probably didn't. Anyways, I did a couple reviews recently, and in it, even though I was doing the noise seeding, I still said that's not what it sounds like to me. So it was arbitrary, but it's what it sounded like to me. But you know what? It's what it sounded like to me.
Yeah.
At best I could figure it out with those two graphs. And to me, I think that's more interesting, right? It's like, I want that kind of honesty about it. I don't need to have it crossing at 500 hertz or 1K, So to me, yeah, anyway.
Yeah.
Sorry if that didn't answer your question.
Okay, last one.
I'm so sorry to keep you guys. I know it's the end of the show, and
Jude, great talk. Sorry to keep everybody else another couple of minutes. So I just got a suggestion. I think there's possibly another explanation for the low frequency.
Sure.
It's lower frequency than we see with the BK system. I'm not entirely convinced about the change in volume.
sure. I don't know why. It's physics, but okay.
With a driver resonance, yes, but for a sealed IEM, like something like the W60 or the Etymotic, if you normalize a thing from like 1K and look down, you really shouldn't see much of a shift in the bass. But I think there are two other things that we need to look at. And if I'm wrong, I'm happy to admit it. I think we need to look at two other things. One is that you've got the squishy outer part of the ear canal. For over ear is no big deal. You're not sealing any air inside the ear canal. But for in ear, you've got a squishy outer part of an ear canal, which is a little bit compliant. And you've also got another issue. You've got this possibility now of, we say, everybody knows the classic thing, you say, well, for an in-ear monitor, it has to be sealed or you don't get bass. but it's not binary. It's not 0 or 1. There's a infinite number of real numbers between 0 and 1 that represents the actual seal that we get with an IEM in our ear.
For an in-ear? I mean, I
For an
pretty
in-ear.
much want a seal for most of them. Yeah.
Yeah, but what I'm saying is, if you take, and this goes both ways. So I think it comes from the direction of the work that B&K have done, and from the work that Sean did on producing the harmonic in the first place, measuring in a solid metal canal. That, from the measurements that we've done, represents sort of the upper limit of what people tend to get with their seal in their ears. But the B&K seems to go a little bit too far in the other direction, and I'm wondering if both those pieces.
But based
of
on
work
what?
had-
Based on what? Based on the fact that we're used to seeing 7-Eleven measurements? Because
No, measurements of actual ears. So when you try to measure in an actual ear and see how difficult it is to get a consistent seal that gets us at a maximum level of
But
bass.
if it was leaking, you wouldn't be flat all the way out to the bottom.
Depends how far. Depends.
No,
depends what kind
It
of
would
leak
roll
you
off.
get.
If you had a leak, it would. I mean, if I'm wrong, Jerry, tell me. But it should roll off. You shouldn't have it flat all the way to 10 hertz or 20 hertz. That's not a leak.
Right, and they actually, Sean tested for that.
Yeah. Well, he's testing. I know he's doing over ears. Is he doing in ears as well?
No, he tested for in-ears as well. He did that with a MEMS mic.
Yeah.
But again.
Oh no,
so
but okay, that I know, and the momentum in ear.
B&K
But
threw away 12 of their 44 samples. Of
Yeah.
those 32 that were left, how good of a quality is it? And I think they did a great job with their work.
But
And I
so
think
you're
diligently
okay.
took those
You're
points.
okay with the work they did in 1980, but not with higher, the
No,
technology
no, no.
and the know-how. And I mean, so for
No,
me,
I'm saying that,
yeah.
that as scientists, we
Yeah.
do the best job we can.
Yeah.
We've got a bunch of data points, and they fit the data, and they produce a new coupler. And it may well be that this is better overall in some kind of average metric than the older 7-Eleven.
Oh, there's no doubt about it.
But-
Okay,
but-
so yeah, but all
What
right.
I'm saying is that the response of the squishy canal, the possibility of not getting a seal, having to throw away 12 of the 44 measurements of the 32 that were left, and the fit that they made, I don't know how representative that is of the average. And
Again, I think a leak would be represented pretty clearly.
the other point is
Yeah.
we may understand about mean, but we don't have a really good grip on variance, which means so we really don't know how useful these measurements are to the average person or the random person rather that picks it up and looks at the graph.
Well, isn't that part of what I was talking about?
Yeah.
That's part of what I was talking about. Yeah, but anyways, yeah.
Okay, guys, we are way over the limit.
So sorry, guys. I'm so sorry. Thanks for sticking around for those who did.
Thanks, Jude.